The points that I wish to cover in this class are, you getting this entire board covered?
Yes, sir.
The points that I wish to cover in this class are, number one, permutations, combinations, then sample space and events, then probability. I think that's it, right? Random variable. We did not do random variable. You guys did not do random variable, right? Yes, Priya? Did you do? No. Anything else that you people have not done? So this is our agenda for the day, right? Let's start with counting. Yes.
I think you also added this random variable.
Conditional probability?
Standard random variable was also there in that class.
Standard normal distribution.
Yeah.
But that we did along with distributions.
That was after, I guess.
Yeah. The only thing that perhaps these guys have missed is conditional probability, but conditional probability I don't think I need to do. Right? Conditional probability is one more thing that we need to do. But in that case, then the lecture will go on for a longer time than the ordinary limit that we have set, 10 o'clock. And then we have the practical registration schedule. So if we can postpone that or postpone it for tomorrow, that's Monday, then we can finish all this today. So you take a call. Fine. Let's start with something like counting. The simple rule of counting is, if there are m outcomes of first experiment, each of the outcomes is associated with n outcomes in the second experiment, then the total outcomes are m into n, or m n outcomes. Okay. So for example, in the third semester, you have 5 electives, 5 options for a paper. Okay. Now, there are 10 students, say 20 students. Each of the students can actually go for 1, 2, 3, 4, 5 options, right? So the possible number of options the students can take is 20 into 5, out of which something they will choose, right? So total number of options are 20 by 5, right? So they are taking these 5. Now in each there are options, but this would be 20 by 5. So first experiment is 20 outcomes, there are 20 students. They have 5 electives to choose. So 20 into 5, whatever the number is, there are so many kind of students by electives combination possible, right? Now we can extend it to a simple rule that if there are m outcomes for the first experiment, n outcomes for the second experiment, for first n outcomes there are r outcomes in, say, next experiment, there will be m, n, p, q, r kind of total outcomes, right? It's a simple principle of counting. Now we go to permutations. How do we decide how many possible options that would exist in or how many different arrangements are possible of n objects? So if there are n objects, in how many different ways those n objects can be put in order, right? Say for example, I have 3 objects, like the example that I took is A, B, C. I have 3 objects. Then these 3 objects can be arranged in multiple ways, right? So ABC is the first way, ACB is the second way. Then I take B in the first position. So BAC and BCA, and I take C at the first position, then CAB and CBA. So what is the logic of doing this? So the 6 different ways in which I can arrange A, B, C, right? 3 objects can be arranged in 6 different ways. So how do I know if I have this number 3 known to me, the 3 objects, how many different ways those 3 objects could be arranged? How many different orders are possible of those 3 objects? Now let's take this example. How many options I have for the first position? I have 3 options. I can put either A at the first position, or B at the first position, or C at the first position, right? Now if I keep A or B or C at the first position, how many options then I have at the second position? 2, right? I'm using the simple principle of counting, multiplying it by 2, right? Once I keep one of the 2 options at the second position, how many options are left at the last position? 1. So this is 3 into 2 into 1, 6. So I have total 6 possible orders of this, right? So these 3 students are sitting here. If I'm saying that this is the first chair, second chair, third chair, then, and if I call them, and if I make one of them sit on the first chair, then any one of them can sit. And so the 3 choices I have for the first chair. Once that first chair is occupied by somebody, I have only 2 people to occupy the second chair. And once the second is occupied, I have only 1 person to occupy the third chair. So these 3 people can sit in 6 possible ways on these 3 chairs, right? Now this is my 3 is my n. I'm doing n into n minus 1, right? Into up to 1, right? This expression is called as n factorial. N factorial, okay? N factorial means n multiplied by n minus 1 multiplied by n minus 2. So n factorial is equal to n into n minus 1 into n minus 2 up to 1, right? As you reach 1, you stop. The convention says that 1 factorial of 1 is 1, and factorial of 0 is also 1. This is by convention. Okay? These are useful conventions while solving problems. Now, this is my all possible orders. Then I can actually ask simple questions that we've discussed earlier. I discuss it again. That if there are 11 players in a cricket team has 11 players, how many batting orders are possible? 11 factorial, right? 11 factorial possible ways of actually batting exist. So 11, the first person, into 10 into up to 2 into 1. Whatever this number is are the possible ways in which actually people can go and bat. It doesn't happen this way because there are people who are batters, there are people who are called as bowlers. So general convention is that people who are good with bat should bat first, and not somebody who is like Umesh Yadav who should open the inning, right? So what we do is we send batters first, we want to send bowlers later, right? So suppose we have 6 people who are batters and remaining 5 are bowlers, right? So even among the batters there will be 5 factorial orders, 6 factorial orders of batters would exist, and 5 factorial orders of bowlers would exist. And so for all those 6 factorial orders, for each of the 6 factorial order of batters, there will be 5 factorial orders of bowlers. So if I take first order of batters, for that particular single order, there will be 5 factorial order of bowlers. For the second order of batters, there will be 5 factorial order of bowlers, so on and so forth. So this is Mn, right? For the first experiment, I have m outcomes. For the second experiment, I have n outcomes for each of the m outcome in the first experiment. So total number of outcomes would be mn outcomes. So this is how I would perhaps, so this number would be slightly smaller than this, right? And so on and so forth. So this is how I can use this principle of permutations to get all possible orders. Now the next thing is combinations. Combinations is not just like permutations, but since we've done this, before I go to combinations, I have a question for you. Okay, all these are these three people are, all of you are sitting in a straight line, right? So these two, you four, and these three people. So 7 plus 2, 9 people are sitting in order. Okay, we assume that 10 people are sitting in order. So how many different ways 10 people can sit in order? 10 factorial, right? 10 factorial ways would exist in which 10 people can sit in order. But suppose they are sitting in a circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Then how many orders would exist? Think about this. The interesting part of this is, suppose this person is sitting here. This person who is ending the order in a straight orders would have a different kind of way. In a sense, if I make it straight line, then this person and this person that come in next to each other doesn't matter for me, right? Right. So, for example, A, B, C, and in some other order, if C comes next to A, doesn't really matter for me in all other ways, but in this it will matter. So I'll have to solve this problem slightly differently. Think, how do we solve this problem? Okay, the next thing is combination. That is selecting n object from n objects, selecting r objects, right? Is what combination is. Now, the problem of combination is very simple. Say, suppose I have 10 people in the front row, or say 5 people in the front row. Okay. Now, out of those 5 people, I have 5 people sitting in the front row. Out of those 5 people, I want some volunteer for some task. Okay, I want say 3 volunteers. Okay, so I have A, B, C, D, E, and F. These are the I took 6. From these 5, I want 3. So I can take A, B, C. I can take A, B, D. I can take A, B, E. I can take. I have done the for combinations of A. Then I can take B, C, D. I can take B, C, E. I can take B, C, E. Right? So B is done. I can take C, D, E. Right? So these are the ways in which I can actually select these people. Right? So how do I actually work it out? How do I actually work it out? Now let's look at this problem slightly differently. How many people I want? I want 3 people. Right? Now how many I have? Whatever I have, the total number of individuals I have are called as n. Okay, what I want is often called as R or X. Okay, I denote it by say R. Okay, so my R is equal to 3, my N is equal to 5. So I want to select R objects from N objects. The condition is R has to be either smaller than or equal to N. It cannot be greater than N because I cannot select 10 people from 5 people, right? So R has to be always smaller than N or equal to N. And if it is equal to N, then there is only one way in which I can select all people from all people, right? So all elements from all elements can be selected in only one way. I take all of them, right? And that's it. Now, let's try and do it. Now, if I select somebody at first positions, how many options I have at the first position?
5.
I have 5 options in this case. Once I am done with those 5 options, how many options I have at the second position? 4. How many options I have at the third position? And done. Right? Done. Now, if I wish to select these many, then it is 5 into 4 into 3, 60. 60. These 60 actually include repetitions. Okay? Repetitions because since I'm doing factorial, I'm repeating some of the orders. Say I take ABC, I'll also take CBA as another order. But if I take ABC, if I select ABC, if I select CBA, number of individuals are same. So out of these 5 individuals, suppose I take these 3 individuals, or her and him, doesn't make a difference because the same 3 individuals are coming. So these orders may be different, but elements are same. So what I'm basically doing is I'm counting some orders again and again. So I need to get rid of it. What are those orders? Those orders are n r factorial, that is 3 into 2 into 1. Okay, so those many orders are being counted again. Now this is to work through this is 60 upon 6 is equal to 10. So there are 10 possible ways I can select 5 people from 3 people from 5 people. Now I select A, B, C, A, C, D, A, D. Sorry, why am I going to C immediately? A, B, D, A, B, E, then A, C, D, A, C, E, and A, D, E. Done? Now, the next is B, C, D, B, D, B, C, E, B, D, E, D is done, and C, D, E. Right? Done? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 ways in which I select 3 people from 3 elements from 5 elements. Right? So actually I have certain number of options at first position, certain number of options at the second position, and so on and so forth. Right? Now, if I start counting A, C, B as another order, another selection, then it's wrong because ABC, when ABC are selected, ACB are also selected. So ACB is no different selection than ABC, and so we need to get rid of this. Now, what is this? How do I express this? This is n, right? N into n minus 1, right? Into up to n minus 1, n minus r plus 1. Right? N minus r plus 1. Okay? That is 3. N minus r is 3. 5 minus 3 is 2 plus 1 is 3, right? So n minus r plus 1, and this is r factorial. This is r factorial, right? So we can actually write this. This is how I get permutations, different. This is how I get combinations. This is how I get r objects from n objects. The easier expression of this is called as n factorial upon r factorial into n minus r factorial, right? N minus r factorial, right? So this is another way of expressing this. This whole thing is called as NCX, denoted as, this is how it's written. It is read as NCX. There are many ways of writing it. People write it as NCX or NCX. These are all identical. So NCX is n factorial upon r factorial into n minus r factorial. That is NCX, that is NCX. Okay? So this is all identical stuff. Yeah.
Should we have an r in place of the x in the expressions like NCX or NCR?
NCR, I'm using r. So, okay. You can use r or x. So if you want r to be written here, I'll write r, and so thank you. But I can write x, r, whatever I wish, and these are identical stuff.
So,
Right?
you remove repetitions only when positional order is not important, right? But if positional order is important,
Then you do permutations.
then you do no.
Permutations. Why? If I want to select elements from, if I wish to select r elements from n elements, why would I be bothered about positional orders? If I am bothered about positional orders, then I take n into n minus 1 up to n minus r plus 1. That's it. These are positional orders of r elements selected from n elements, keeping all positional orders intact. If I am not interested in positional orders, I divide it by r factorial. If I am interested in keeping the positional orders intact, I don't need this denominator. I'll keep the numerator, and that's my positional orders. Then all those things like ACB, BCA, all such things like, see, ABC can be ordered in 6 possible ways, right? We have seen ABC can be ordered in 6 possible ways. So all those 6 possible ways would come, right? These 3 can be ordered into 6 possible ways. These 3 are possibly ordered in 6 possible ways, right? So if so there are 10, these are 10, which can be possibly ordered in 6 possible ways, so I get 60, right? So what is this? This is n into n minus 1 up to n minus r plus 1, right? Right? So these are all possible orders. I want to remove the permutations of each of them. Each of them take r factorial permutations. Each of the order takes r factorial permutations. They are counted here. So I want to remove them. So I divide it by r factorial. Right? Understood? See, this ACD can be also written as ADC or CAD or CDA or DAC or DCA. 1, 2, 3, 4, 5 and 6. So this this expression is counting all these 6 per order. Okay, and I want to get rid of this. So this I am getting by r factorial, right? So I don't want them, so I divide it by r factorial. R is 3. 3 factorial is 3 into 2 into 1. 3 into 2, 6 into 1, 6. Right? Easy to understand? Yeah. So this is permutations. Have you understood why we wrote it this way? This expression? You've understood, right? Is there anyone who's not followed? See, pretty simple. What did I write to begin with? I wrote NCR is equal to n minus 1, n into n minus 2, n minus r plus 1, right, upon r factorial. Now, if I write this entire thing as n factorial, then I am writing certain thing extra. Okay, if I write n factorial in the numerator, then what is n factorial? N factorial would go up to 1. Okay, so this is a point. This is n minus r plus 1. Then this is n minus. If I have to write this way, then I would write n factorial as. If I write n factorial as a numerator, it would be n into n minus 1 into n minus 2 up to n minus r plus 1 into n minus r into n minus r minus 1 into say 1, right? Up to 1, right? If I divide it by r factorial, what I am doing extra in the numerator is, I want to stop here. What I am doing in r to 1, n minus r to 1 is n minus r factorial. I don't want this, right? This is n minus r factorial, right? So what I need to do is I need to divide this numerator by n minus r factorial. So this is my n factorial. So my numerator is n factorial, denominator is r factorial into n minus r factorial, right? It is stopped working. Now next point is, so we have done the permutation combination, the very basic part of it, right? Next is sample space in event. Okay, what is sample space? Sample space is when you have all possible, is a set that consists of all possible events. Sample space is a set that consists of all possible events. Okay, say for example, if you are rolling a die or you are tossing a coin. If you toss a coin, then